An expectation that when humanity finally built a telescope powerful enough to look directly into the earliest eras of the universe, the story it revealed would be simple, primitive, quiet. A slow beginning that gradually grew into the complexity seen today. For decades, that assumption rested comfortably inside the models that described how stars formed, how galaxies assembled, and how structure slowly emerged from an almost uniform sea of hydrogen and helium. Then the James Webb Space Telescope opened its mirrors. It now sits far beyond Earth, positioned in a gravitational balance point where the Sun, Earth, and deep space allow it to remain shielded from heat and interference. From that cold, distant vantage point, its instruments collect ancient light that has been traveling across the expanding universe for billions of years. Each photon it records is not just an image, but a message from a time when the cosmos was young. Looking deeper into space is not simply looking farther away. It is looking backward. The greater the distance, the earlier the moment being observed. At the most extreme ranges, the telescope is examining regions that existed only a few 100 million years after the beginning of cosmic expansion. Before Webb, the expectation was clear. The early universe should have appeared dark, sparse, and dominated by small, simple structures. The first stars would ignite slowly. The first galaxies would begin as faint, irregular clusters gradually growing through mergers and gravitational accumulation. Complexity was supposed to take time. Instead, the first deep observations revealed something that did not fit that quiet narrative. Where astronomers expected to see scattered fragments of young galaxies, Webb began detecting systems that appeared surprisingly large, bright, and organized. These objects were not impossible according to physics, but they were far more mature than many simulations had predicted for that stage of cosmic history. Some of these galaxies appear at redshifts, indicating they existed when the universe was only a few 100 million years old. Their light shows structures that suggest significant star formation had already occurred. In some cases, the inferred stellar mass is much higher than models anticipated for that epoch. It is not that the universe broke its own rules. It is that the timeline may have been more efficient than expected. Earlier telescopes could only hint at these distant objects. Their sensitivity was limited, their resolution blurred. Webb, operating in infrared wavelengths, can see through dust and detect faint signals stretched by cosmic expansion. Suddenly, what once looked empty revealed density. The surprise was not the existence of galaxies. It was how quickly some of them seemed to assemble. Simulations of early cosmic evolution predicted that the first generations of stars would form from collapsing clouds of primordial gas. These early stars would then enrich their surroundings with heavier elements through explosive deaths. Only after several cycles would larger, chemically mature galaxies begin to dominate. Yet Webb's spectroscopic measurements indicate that some early systems already contained signatures suggesting rapid stellar processing. The chemical fingerprints are subtle, still debated, but they point toward star formation happening earlier or more efficiently than previously assumed. In science, that kind of discrepancy does not imply error in the laws of physics. It signals that the initial conditions or growth rates may need refinement. And the pattern did not appear only once. Multiple independent observations began to show that early galaxies were not rare anomalies scattered across the sky. When deep fields were examined repeatedly, similar candidates appeared again. Some were compact and intensely bright. Others showed hints of disk-like structure that normally takes longer to stabilize. Each new dataset forced astronomers to ask a quiet but persistent question. Was the early universe simply better at building structure than expected? The answer is not yet settled, but the tension is real. If galaxies assembled faster, then either star formation was more efficient, Or the distribution of matter after the beginning of cosmic expansion contained denser seeds than current simulations assumed. That tension extends beyond galaxies themselves. At the centers of many modern galaxies sit supermassive black holes containing millions or billions of times the mass of the Sun. Conventional growth models suggest that such objects begin as smaller remnants of massive stars and gradually accumulate matter or merge with other black holes over long timescales. Webb has contributed to the growing body of evidence that some extremely massive black holes existed earlier than once expected. Observations of ancient quasars indicate that within less than 1 billion years, certain black holes had already reached enormous masses. Their accretion disks glow with energy output capable of outshining entire galaxies. The existence of these early giants does not violate relativity or gravitational theory. However, their rapid growth requires either unusually efficient feeding processes, very massive initial seeds, or mechanisms such as direct collapse of enormous gas clouds. Each explanation is plausible. None is yet universally confirmed. This is the kind of tension that drives modern astrophysics. Not contradiction, not crisis. A narrowing gap between prediction and observation. Even the distribution of matter itself is being examined with new clarity. Gravitational lensing measurements allow Webb to observe how foreground mass bends the light of more distant objects. These distortions help map invisible structures dominated by dark matter. Early observations suggest that some regions of the young universe contained significant concentrations of matter earlier than expected in certain models. Again, not impossible, just earlier. This pattern repeats across multiple datasets. Structure formation, star formation efficiency, and early mass assembly all appear slightly accelerated, compared with older expectations built from limited observational reach. The result is not a collapse of cosmology. It is refinement, and refinement can feel unsettling. For decades, the broad outline of cosmic history seemed settled. The universe expanded from a hot, dense state. Matter gradually clumped. Stars ignited. Galaxies formed. Complexity emerged over billions of years. Webb is not rewriting that story. It is sharpening the details. Where earlier observations suggested a smooth progression, the deeper view reveals bursts of rapid development. Regions where gravity worked faster. Environments where gas collapsed more efficiently. Pathways that simulations had not fully captured. Each new image is both confirmation and correction. The early universe was not empty. It was active. And every additional observation seems to reinforce that activity was already underway, far sooner than once assumed. What makes this moment historically significant is not that Webb found something impossible. It is that the first truly high-resolution view of cosmic infancy is forcing scientists to reconsider how quickly complexity can arise when the right conditions exist. In the coming years, repeated observations, improved spectroscopy, and cross-checks with other instruments will determine whether these early galaxies represent the norm or the extreme edge of formation. For now, the tension remains. A universe that appears to have grown up slightly faster than predicted. If the early galaxies were the first hint that the universe matured faster than expected, the next discovery sharpened that tension even further. At the centers of many modern galaxies sit objects so dense that not even light can escape their gravity. Supermassive black holes containing millions or even billions of times the mass of the Sun are now understood to be a common feature of large galactic systems. In the nearby universe, their existence feels almost routine. In the distant past, their presence becomes far more difficult to explain. Traditional models describe a gradual process. Massive stars collapse and leave behind smaller black holes. Those remnants merge, accrete surrounding gas. and slowly grow across immense spans of time. Even under optimistic conditions, reaching extreme mass requires sustained feeding over hundreds of millions or billions of years. Yet observations of very distant quasars indicate that some of these giants were already in place when the universe was still comparatively young. A quasar is not simply a bright point of light. It is a galaxy whose central black hole is actively consuming matter. Gas spirals inward, heats to extraordinary temperatures, and releases vast amounts of energy before crossing the event horizon. The resulting luminosity can exceed the combined output of entire galaxies. Long before Webb, astronomers had already detected quasars from early epochs. What Webb contributes is clarity and context. Its infrared sensitivity allows researchers to examine their host galaxies and environments with greater precision than was previously possible. Some of these ancient quasars appear at distances corresponding to less than 1 billion years after cosmic expansion began. Their central black holes already contain hundreds of millions, sometimes approaching 1 billion solar masses. This does not violate known physics. Black holes can grow rapidly if they are supplied with enough material. The tension lies in how such efficient growth could occur so early. One possibility involves unusually massive initial seeds. Instead of forming from the collapse of individual stars, enormous clouds of gas may have collapsed directly into black holes, tens of thousands of times the mass of the Sun. Starting larger reduces the amount of growth required. Another explanation considers sustained periods of extremely rapid accretion. Under certain conditions, matter can fall inward at rates approaching theoretical limits without blowing itself away through radiation pressure. If those feeding phases lasted long enough, rapid early growth becomes plausible. There is also the role of dense environments. If early galaxies were more compact and gas-rich, the available fuel supply would have been abundant. Repeated mergers between proto-galaxies could channel matter directly towards central regions, accelerating the process. None of these ideas break established theory. Each remains an active area of investigation, supported by simulations that attempt to reproduce the observed masses. What changes with Webb is the statistical weight of the evidence. Instead of a few rare examples, astronomers are identifying multiple early systems that contain unexpectedly massive central objects. The pattern suggests that accelerated black hole growth may not have been unusual under early cosmic conditions. When the telescope examines the surrounding galaxies, another detail becomes visible. Some host galaxies appear relatively small compared with the mass of their central black holes. In the modern universe, there is usually a strong relationship between the size of a galaxy and the mass of the object at its core. These early systems sometimes seem to be out of balance. That imbalance hints that black holes may have grown faster than the galaxies around them. If true, it suggests that the early stages of cosmic evolution allowed gravity to concentrate matter in central regions with remarkable efficiency. The familiar relationship between galaxies and their cores may have emerged later, after billions of years of interaction and regulation. The energy output from these feeding black holes also shapes their surroundings. Intense radiation and outflows can heat gas, trigger or suppress star formation, and influence how the host galaxy evolves. Observing that feedback in early systems provides a glimpse into how structure formation unfolded under extreme conditions. Webb's spectroscopic instruments can analyze the light from these distant quasars and measure the motion of surrounding gas. The data reveal turbulent environments where matter is moving at enormous velocities, tracing the gravitational influence of unseen mass. Each measurement refines estimates of black hole size, feeding rate, and local density. What emerges is not a contradiction, but a more dynamic picture of the early universe than previously assumed. Rather than a slow and orderly build-up, certain regions appear to have undergone rapid gravitational collapse. Dense pockets of matter formed stars quickly, channeled gas inward, and created central engines capable of reshaping entire galaxies. This accelerated phase may have been brief on cosmic timescales, but its impact appears profound. The presence of early supermassive black holes also intersects with broader cosmological questions. Their intense radiation contributes to the process known as reionization, when ultraviolet light from the first luminous objects transformed the surrounding hydrogen from neutral gas into an ionized plasma. Understanding how much quasars contributed compared with early stars is still under investigation. Webb's ability to detect faint surrounding structures helps estimate how widespread these energetic sources were. Again, the tension is subtle rather than catastrophic. The universe still follows known gravitational and thermodynamic principles. The difference lies in efficiency. Matter appears to have organized itself into extreme structures earlier and more energetically than earlier datasets suggested. Each new observation tightens constraints on simulations. Models must now reproduce not only the existence of early galaxies, but also the rapid appearance of massive central engines capable of powering quasars visible across billions of light years. This process of refinement is familiar in the history of astronomy. When better instruments appear, the universe rarely becomes simpler. Instead, it reveals layers of complexity that were always present but previously hidden by distance, dust, or limited sensitivity. The early cosmos, once imagined as quiet and sparse, now appears crowded with activity. Galaxies assembling, stars igniting, black holes feeding, radiation reshaping the surrounding medium. A period that once felt like a slow beginning increasingly resembles a time of intense construction. And with each additional deep field survey, the pattern persists. Early massive galaxies, early chemical enrichment, early central black holes. None of these discoveries overturn the framework of cosmic evolution. Together, they suggest that the first few 100 million years may have been more efficient at building structure than many models anticipated. That realization carries an important implication. If complexity can emerge rapidly under the right conditions, then the universe did not spend its infancy in prolonged darkness. It transitioned into a structured luminous state sooner, and perhaps more unevenly, than previously mapped. Webb continues to extend that nap. Every faint quasar detected at extreme distance is another data point anchoring the timeline. Each spectrum adds constraints on how quickly matter can collapse, ignite, and concentrate under gravity. The telescope is not revealing impossibilities. It is revealing that the early universe was already busy. And as observations accumulate, the question is no longer whether massive black holes existed early. It is how many formed, how quickly they grew, and what conditions allowed them to do so. If early galaxies and unexpectedly massive black holes suggest that matter gathered more efficiently than expected, the light from those same systems reveals another layer of acceleration. The earliest universe began with remarkable simplicity. In the aftermath of expansion from its hot, dense origin, the available elements were limited almost entirely to hydrogen and helium, with only trace amounts of lithium. Everything heavier, every atom that makes planets, oceans, and living systems possible, had to be created later inside stars. The process is well understood. Nuclear fusion inside stellar cores gradually builds heavier elements. When massive stars reach the end of their lives, they explode and scatter those newly formed materials into surrounding space. Subsequent generations of stars incorporate that enriched gas, slowly increasing chemical complexity across cosmic time. That cycle was expected to take hundreds of millions of years before leaving detectable signatures on a large scale. Yet Webb's spectroscopic observations of some extremely distant galaxies indicate that chemical enrichment was already underway earlier than anticipated in several regions. When light from these galaxies is spread into its component wavelengths, distinct absorption and emission features appear. These features act like fingerprints, revealing the presence of elements such as oxygen, carbon, and in some cases heavier metals. The detections remain cautious and are still being refined through repeated observation, but the pattern is consistent enough to prompt careful reassessment of early stellar activity. The implication is not that heavy elements appeared instantly, but that the first generations of stars may have formed, lived, and ended their lives more rapidly than older simulations assumed. Massive stars burn through their fuel quickly. Their lifespans can be measured in only a few million years. If the earliest star-forming regions produced large numbers of these short-lived giants, the first chemical enrichment phase could have progressed faster than previously modeled. This scenario aligns with the idea that early gas clouds were dense and unstable, collapsing into stars with higher average masses. Such an environment would accelerate both energy output and the recycling of matter into subsequent stellar populations. Webb's sensitivity allows these faint chemical signals to be detected across enormous distances. Earlier instruments could only confirm the presence of distant galaxies. Now, the composition of those galaxies can be examined with far greater precision. In several candidate systems, the spectral lines suggest that the surrounding gas is not purely primordial. Instead, it appears to have already been influenced by prior stellar generations. This observation adds weight to the emerging pattern. The early universe was not chemically stagnant for long. Star formation appears to have ignited in concentrated pockets, producing bursts of activity that enriched nearby space at a pace faster than many earlier estimates. These findings do not overturn nuclear synthesis theory. The physics of fusion remains unchanged. The difference lies in the timing and scale of the first stellar populations. If the first stars formed sooner and in greater numbers, the resulting chemical evolution would advance accordingly. Another factor under investigation is the efficiency with which early galaxies retained or lost enriched material. In smaller systems, supernova explosions can push heavy elements outward, dispersing them across intergalactic space. In more massive or tightly bound systems, that material may remain gravitationally contained, accelerating the buildup of complexity. Webb's data suggests that some early galaxies possessed sufficient gravitational structure to hold onto enriched gas. That retention would allow subsequent star formation to occur in already processed material, shortening the pathway toward chemical maturity. This accelerated enrichment has broader consequences. Heavier elements influence how gas cools. Metal, enriched gas, radiates energy more effectively, allowing it to collapse into new stars with greater efficiency. In this way, early chemical evolution feeds back into structure formation, increasing the pace at which galaxies grow. The result is a reinforcing cycle. Rapid star formation produces heavy elements. Those elements enhance cooling. Enhanced cooling produces additional star formation. What once appeared to be a slow and uniform process now looks more episodic and concentrated, with regions of intense activity shaping their surroundings. Webb's deep field surveys are gradually mapping how widespread these enriched systems were. Some appear isolated. Others are located in environments dense with neighboring structures, suggesting early clustering. The emerging picture is not one of contradiction, but refinement. The early cosmos contained pockets where gravity, density, and available gas combined to produce rapid bursts of stellar evolution. These regions matured quickly, while other areas remained comparatively primitive. This uneven development may explain why some observations reveal highly evolved galaxies, while others still appear faint and irregular. Chemical signatures also provide insight into the life cycle of the first stellar populations. By comparing abundance ratios, astronomers can estimate whether enrichment came primarily from extremely massive stars or from multiple generations of smaller ones. Early indications suggest that the first stars may have included a significant population of massive, short-lived objects capable of producing heavy elements efficiently. If confirmed, this would help reconcile the presence of enriched gas with the relatively short time available. The importance of these measurements extends beyond composition alone. Chemical fingerprints also affect how astronomers estimate distances, star formation rates, and the age of stellar populations. As Webb refines these readings, the timeline of early cosmic development becomes increasingly detailed. Each improved spectrum acts like a historical record, encoded in light, that began its journey billions of years ago. The tension, once again, is subtle rather than dramatic. Nothing observed requires new physics. Instead, the data suggests that the early universe was more efficient at producing complexity than older models, constrained by limited evidence, had indicated. The first few 100 million years may have contained rapid cycles of birth, collapse, and enrichment, occurring in concentrated regions that were previously invisible to observation. From a distance of billions of light-years, those early processes now appear frozen in time, their signatures carried across expanding space until intercepted by Webb's mirrors. The effect is similar to opening an archive that was always present but unreadable. What once looked like a dim, featureless background now resolves into structured environments already undergoing transformation. With each additional observation, astronomers refine their simulations to account for these accelerated pathways. And as those models adjust, another question naturally follows. If matter could assemble, ignite, and chemically evolve earlier than expected in localized regions, then the distribution of invisible mass that guided those processes becomes even more important to understand. Because beneath every galaxy, every burst of star formation, and every region of early enrichment lies the gravitational framework that shaped where matter gathered in the first place. That framework is dominated not by visible stars or gas, but by something that does not emit light at all. Beneath every bright galaxy Webb observes, beneath every cluster of stars and every region already rich with heavy elements, there exists a deeper architecture that cannot be seen directly. Gravity reveals it. Long before any telescope could detect ancient starlight, cosmologists understood that most of the matter shaping the universe is invisible. This unseen component, known as dark matter, does not emit or absorb light. It interacts primarily through gravity, forming the scaffolding upon which visible structures assemble. Without it, galaxies would not hold together. Clusters would disperse. The large-scale pattern of the universe would look entirely different. Webb does not observe dark matter directly, yet its influence appears everywhere in the data. When the telescope looks at extremely distant galaxies, it often sees distorted shapes, stretched arcs, or multiple mirrored images of the same object. These distortions occur because massive concentrations of matter bend the path of light traveling across cosmic distances. This effect, known as gravitational lensing, acts like a natural magnifying glass embedded in space itself. By carefully measuring those distortions, astronomers can map the distribution of mass that caused them, including the portion that remains invisible. In several early fields examined with Webb's instruments, the inferred mass concentrations appear substantial even at very early cosmic times. The lensing signatures suggest that dense structures were already present when the universe was still in its infancy. Again, the observation does not contradict theory. Dark matter is expected to collapse into clumps first, guiding the later formation of stars and galaxies. What appears to be shifting is the pace at which some of those clumps grew. Simulations predicted that small fluctuations in the density of matter would gradually amplify under gravity, forming larger and larger halos across hundreds of millions of years. Webb's measurements indicate that in certain regions, those halos may have reached significant mass sooner than many earlier models suggested. If the invisible framework formed quickly, it would naturally accelerate everything built upon it. Gas would fall inward faster. Star formation would ignite sooner. Galaxies would assemble with greater efficiency. This relationship between dark matter distribution and visible structure is now being re-examined with Webb's increasingly precise observations. In deep survey regions, early galaxies are sometimes found grouped along faint alignments that hint at filamentary structure. These alignments resemble segments of what is known as the cosmic web, a vast network of dark matter filaments that connects clusters across enormous distances. In the nearby universe, this web is clearly mapped through large-scale surveys. Filaments stretch across hundreds of millions of light-years, guiding the flow of gas and galaxies toward dense nodes. Seeing hints of similar organization in extremely distant epochs suggests that at least parts of this network were already taking shape earlier than expected. The early universe may not have been a uniform mist slowly condensing everywhere at once. Instead, structure appears to have developed unevenly, with certain regions becoming gravitational hubs while others remained comparatively empty. Webb's sensitivity allows faint background galaxies to be used as probes of intervening mass. By examining how their light is distorted, astronomers reconstruct the invisible landscape lying between observer and source. These reconstructions reveal concentrations of mass that cannot be explained by visible matter alone. In some cases, the estimated dark matter halos surrounding early galaxies appear more massive relative to their visible stars than similar systems observed closer to the present era. This does not mean dark matter behaves differently. It suggests that the ratio between collapsed invisible mass and newly formed stars may have been higher during the earliest stages of structure formation. As star formation progressed and galaxies merged, the visible component would gradually increase, producing the more familiar relationships measured today. The idea that the first gravitational wells were deep and efficient aligns with the earlier observations of rapid galaxy assembly and accelerated chemical enrichment. Dense halos gather gas. Gas forms stars. Stars enrich their surroundings. Each layer reinforces the next. The telescope is also contributing to the ongoing effort to map how matter is distributed across vast distances through statistical surveys. By counting how many galaxies appear at different brightness levels and redshifts, astronomers infer how structure evolved over time. Initial results suggest that the numbered density of certain early systems may be higher than predicted by earlier, less sensitive observations. This does not imply that previous measurements were incorrect. It reflects the fact that many faint objects simply could not be detected before. With improved sensitivity, the census becomes more complete. That expanded census feeds directly into models describing how the universe's expansion and matter distribution interact. The expansion rate itself remains a subject of careful measurement. Independent methods have produced slightly different values, a discrepancy often referred to as the Hubble tension. While Webb was not designed primarily to resolve that issue, its precise infrared observations of distant standard candles and galaxy properties provide additional data points that may help refine distance estimates. Even small adjustments to expansion history can influence how quickly structures are expected to grow. In this way, each new observation contributes to a tightly interconnected framework. Dark matter distribution influences galaxy formation. Galaxy formation affects chemical evolution. Chemical evolution influences cooling and subsequent structure growth. Expansion rate measurements affect the predicted timeline of all of these processes. Webb is now supplying higher resolution data across each layer simultaneously. What emerges is not a universe behaving unpredictably, but one revealing subtleties that were previously beyond reach. The early cosmic web appears to have begun organizing matter into channels and nodes earlier than many simulations captured. Those channels would have directed gas toward dense regions, fueling the bursts of star formation already observed. Where matter accumulated efficiently, galaxies matured quickly. Where density remained low, development lagged behind. This uneven progression leaves a fossil record visible in the distribution of distant systems. Some deep fields show clusters of surprisingly bright galaxies. Others reveal sparsely populated regions where only faint objects appear. Together, these patterns reinforce the idea that early cosmic history was not uniform. It was structured, dynamic, and regionally diverse. Each gravitational lens, each faint alignment of distant galaxies, provides another clue to how invisible matter sculpted the visible universe. As additional survey data accumulates, astronomers continue refining simulations that track billions of particles under gravitational interaction across cosmic time. These models are now being recalibrated to match the higher abundance of early massive systems and the inferred density of early dark matter halos. The process is iterative. Observation informs simulation. Simulation predicts new signatures. New observations test those predictions. With Webb's reach extending deeper into infrared wavelengths, even fainter background sources become visible, improving the precision of mass mapping. The result is a progressively sharper image of the universe's underlying skeleton. And as that skeleton becomes clearer, another realization follows. If gravity organized matter efficiently at early times, then the transition from darkness to widespread illumination may have occurred faster and across more regions than once assumed. The period once described as a long cosmic twilight begins to look more like a patchwork of rapidly igniting lights. Regions collapsing under gravity, forming stars, enriching gas, and shaping the surrounding medium almost simultaneously across vast distances. The early universe was not waiting. It was already building. One of the most powerful ways to understand the universe is not through a single dramatic image, but through repetition. Point the telescope at different regions. Measure the same properties again and again. Count what appears, compare it with what should have appeared, and look for patterns that persist across independent observations. This is where the deepest surveys from Webb begin to shift the conversation from isolated surprise to statistical tension. The first widely released deep field image focused on a region containing the galaxy cluster commonly used for gravitational lensing studies, revealed dense backdrop of distant systems extending far beyond what earlier instruments could resolve. At first, the presence of unexpectedly bright early galaxies was treated cautiously. A single field can always contain anomalies. But Webb did not stop with one field. Subsequent observing programs examined additional patches of sky with similar depth. Different teams, using independent analysis pipelines, began identifying candidate galaxies at extreme distances across multiple regions. What mattered was not any individual object. It was the consistency. Across these separate fields, astronomers repeatedly detected galaxies whose inferred brightness and estimated stellar mass placed them at the higher end of what earlier simulations predicted. The distribution did not appear dominated by a few rare outliers. Instead, the number of luminous candidates suggested that rapid early structure formation may have been relatively common in certain environments. This shift from singular discovery to repeated detection changes how evidence is weighed. When only one or two distant galaxies appear unusually mature, measurement uncertainty or rare formation pathways remain likely explanations. When similar systems appear across independent surveys, the probability that the models themselves need adjustment increases. Webb's infrared capability is critical in this process. Light emitted in the ultraviolet and visible ranges billions of years ago has been stretched by cosmic expansion into longer wavelengths. Earlier telescopes could detect only the brightest examples. Webb's sensitivity reveals objects that were previously invisible, expanding the sample size dramatically. With a larger sample, statistical analysis becomes meaningful. Astronomers can now compare observed galaxy counts at different redshift ranges, with predictions generated by large-scale cosmological simulations. Early results suggest that certain brightness ranges contain more galaxies than expected under earlier parameter assumptions. This does not imply that the theoretical framework is incorrect. It indicates that the efficiency of star formation, the distribution of early dark matter halos, or the initial density fluctuations may require recalibration. Repeated deep field observations also reduce the risk of misidentifying closer objects as distant ones. Spectroscopic follow-up allows precise measurement of redshift, confirming whether candidates truly belong to the early universe. As confirmed distances accumulate, confidence in the revised population statistics grows. Another emerging pattern involves the diversity of early galaxy morphology. Some distant systems appear compact and irregular, consistent with early assembly. Others show hints of rotational structure or disk formation, suggesting that organized motion developed earlier in certain environments than previously assumed. The variety itself is informative. If early galaxies formed through a range of pathways, then the timeline of structure formation was likely more complex than a single smooth progression. Repeated surveys also reveal clustering tendencies. Rather than appearing randomly distributed, some early galaxies are located near one another, suggesting shared underlying dark matter structures. These localized concentrations reinforce the idea that gravitational collapse created regions of accelerated development while leaving other areas comparatively sparse. By mapping multiple deep fields, astronomers can begin constructing a three-dimensional picture of how these early clusters relate to the larger cosmic web. Another benefit of repeated observation is improved calibration. Initial photometric estimates of brightness and mass carry uncertainty. With additional exposures and longer integration times, noise decreases and measurements become more precise. Objects that once appeared exceptionally massive may shift slightly downward. Others may be confirmed as even more luminous than first estimated. This refinement process is essential. Science rarely advances through a single definitive measurement. It progresses through repeated verification, gradual tightening of error margins, and the accumulation of independent confirmations. Webb's observing schedule reflects this philosophy. Programs designed to revisit previously studied fields allow astronomers to track consistency across instruments, filters, and analysis techniques. Each iteration strengthens confidence in the resulting population statistics. As datasets grow, simulation teams incorporate the new counts into updated models of early galaxy formation. Adjustments may include higher star formation efficiency in dense halos, altered feedback mechanisms from early black holes, or revised assumptions about the distribution of primordial density fluctuations. These refinements do not erase previous understanding. They sharpen it. Another subtle but important effect of repeated deep field surveys is the detection of faint background galaxies that were initially below the noise threshold. As integration time increases, the faint end of the luminosity distribution becomes clearer. Understanding how many small, dim galaxies existed alongside brighter ones is crucial for estimating how much radiation was produced during the universe's early luminous phase. The combined output from numerous faint systems may have played a significant role in transforming the surrounding hydrogen from neutral to ionized. In this way, repeated observation does more than count bright anomalies. It reconstructs the full ecosystem of early cosmic structures. Some regions appear dominated by a few massive systems. Others contain numerous faint galaxies that collectively contribute substantial energy output. Mapping that variation provides insight into how the first large-scale transformations unfolded. Another layer of tension emerges when comparing observational results with different simulation suites. Models tuned to match earlier telescope data sometimes underpredict the abundance of certain early galaxies. Updated simulations that incorporate revised star formation parameters often align more closely with Webb's counts. This iterative feedback loop between observation and modeling is expected. Each generation of instruments extends the observable frontier, revealing complexity that requires theoretical adjustment. The pattern has repeated throughout the history of astronomy. New technology expands the horizon. The universe appears more structured than previously measured. Models evolve to match the improved data. What makes the current moment distinctive is the scale of improvement. The jump in sensitivity between previous infrared observatories and Webb allows exploration of epochs that were once accessible only through indirect inference. Now, those epochs are being sampled directly. Repeated deep field surveys transform speculation into measurement. Instead of extrapolating from a handful of distant points, astronomers can construct population distributions, examine clustering statistics, and trace how brightness and structure evolve across redshift ranges. The emerging picture is one of early diversity and rapid regional development. Some sectors of the young universe appear to have hosted vigorous star formation and significant mass assembly. Others remained comparatively quiet. That uneven growth leaves an imprint detectable billions of years later. Each deep field becomes a window into a different chapter of that process. Together, they form a mosaic of early cosmic history. And as the mosaic fills in, the narrative becomes clearer. The early universe was not defined by uniform gradual change. It was shaped by pockets of intense activity embedded within a larger expanding framework. Repeated observation turns that impression into measurable evidence. With each additional survey, confidence increases that the accelerated formation of certain galaxies and black holes was not an isolated curiosity. It was part of a broader pattern. A pattern that suggests gravity, density, and available fuel combined in some regions to produce complexity faster than earlier models anticipated. As this statistical foundation strengthens, attention naturally shifts toward the next question. If the first luminous structures appeared earlier and more energetically than once mapped, how did their combined radiation transform the surrounding medium and reshape the universe on the largest scales? Long before the first galaxies became common across the sky, the universe passed through a period often described as its longest quiet phase. After the initial expansion and cooling, matter existed primarily as neutral hydrogen and helium gas. Light could travel freely, but there were few sources bright enough to illuminate the darkness. This era, sometimes called the Cosmic Dark Ages, ended only when the first stars and energetic systems began to ignite. What followed was a transformation known as Reionization. As the earliest luminous objects formed, they emitted intense ultraviolet radiation. That radiation interacted with surrounding hydrogen atoms, stripping away electrons and converting neutral gas into an ionized state. Once enough regions underwent this change, the universe became increasingly transparent to high-energy light. Understanding exactly when and how quickly this transition occurred has been one of the central goals of modern observational cosmology. Webb is now providing some of the clearest evidence yet of how that process unfolded. By detecting extremely distant galaxies across a range of redshifts, astronomers can estimate how much ionizing radiation was being produced at different moments in early cosmic history. The number, brightness, and distribution of these galaxies determine whether there were enough energetic sources to transform the surrounding medium. Repeated deep-field observations suggest that the early universe contained more star-forming systems than previously confirmed with earlier instruments. Even many faint galaxies, individually modest in output, collectively contribute substantial ultraviolet radiation. When considered together, these populations may account for a significant portion of the energy required to ionize vast regions of intergalactic gas. Spectroscopic measurements also reveal the state of hydrogen along the line of sight to distant objects. In some cases, the absorption features indicate that large volumes of space had already transitioned from neutral to ionized, earlier than older datasets implied. The process was likely uneven. Rather than a single global event, reionization appears to have progressed through expanding bubbles of ionized gas surrounding clusters of early galaxies, quasars. These bubbles gradually merged, creating larger transparent regions, while isolated pockets of neutral hydrogen persisted longer in less active areas. Webb sensitivity allows astronomers to identify galaxies embedded within partially ionized environments, providing snapshots of different stages. Within this transformation, in some fields, early galaxies appear surrounded by regions where hydrogen absorption is reduced, suggesting local ionization had already taken hold. In others, strong absorption signatures remain, indicating that the surrounding medium was still largely neutral. This patchwork pattern reinforces the emerging theme. The early universe was not evolving uniformly. Dense regions hosting vigorous star formation began reshaping their surroundings quickly. More isolated regions lagged behind, transitioning later as radiation from nearby sources eventually reached them. The presence of early quasars adds another layer. Accreting black holes emit intense high-energy radiation capable of ionizing large volumes of gas. Even if they were less numerous than ordinary star-forming galaxies, their individual output could influence the structure of surrounding intergalactic space across vast distances. Webb's observations of these energetic systems help constrain how much they contributed relative to stellar populations. Together, the combined evidence suggests that the universe may have become transparent somewhat earlier, and in a more complex pattern than earlier models based on limited data indicated. This does not overturn the established framework of cosmic evolution. Instead, it fills in the missing details of a transition that had previously been inferred mostly from indirect measurements. By mapping galaxies across multiple redshift intervals and examining the state of intervening hydrogen, astronomers are gradually reconstructing how the first widespread illumination spread through space. Each newly confirmed distant galaxy acts as both a source of radiation and a probe of the medium between observer and origin. The result is a layered timeline. At first, isolated stars ignite within dense halos. Their radiation creates small ionized pockets. As more galaxies form, those pockets expand and overlap. Eventually, large continuous regions of ionized gas dominate, allowing light to travel across vast distances with less obstruction. The period once imagined as a slow fade from darkness increasingly appears as a complex, regionally driven transformation. The first light did not arrive everywhere at once. It spread outward from the earliest structures, gradually reshaping the universe's transparency and setting the stage for the richly structured cosmos observed today. Webb continues to extend this timeline further back, identifying ever fainter galaxies that contributed to that process. With each additional detection, the transition from darkness to illumination becomes less abstract and more directly measured. The early universe was not waiting in silence. It was already brightening, region by region, as gravity gathered matter, stars ignited, and radiation pushed back the remaining neutral fog. The deeper the James Webb Space Telescope looks, the less the early universe resembles the quiet, gradual beginning once imagined from limited evidence. What emerges instead is a period marked by rapid structure formation, energetic environments, and localized bursts of development that shaped everything that followed. None of these observations overturn the foundation of modern cosmology. The broad outline remains intact. The universe expanded from a hot, dense origin. Matter condensed under gravity. Stars formed. Galaxies assembled. What has changed is the resolution of that story. Early galaxies appear sooner and in greater variety than earlier surveys could confirm. Some regions show unexpectedly efficient star formation and rapid chemical enrichment. Massive black holes were already influencing their surroundings. Dark matter halos provided deep gravitational wells that accelerated collapse in certain environments. Repeated deep field observations have transformed isolated surprises into measurable population trends. The first luminous structures did not emerge slowly everywhere at once. They ignited unevenly, creating pockets of intense activity embedded within a larger expanding framework. Those pockets produced the radiation that gradually ionized the surrounding hydrogen, turning a once opaque universe into one increasingly transparent light. Each of these findings narrows the gap between theoretical prediction and observed reality. Where earlier models relied heavily on extrapolation, direct measurement is now possible across epochs that were once beyond reach. The result is not a universe behaving unpredictably, but one revealing that its earliest chapters were more dynamic than previously mapped. This refinement, there was always an expectation that when humanity finally built a telescope powerful enough to look directly into the earliest eras of the universe, the story it revealed would be simple, primitive, quiet. A slow beginning that gradually grew into the complexity seen today. For decades, that assumption rested comfortably inside the models that described how stars formed, how galaxies assembled, and how structure slowly emerged from an almost uniform sea of hydrogen and helium. Then the James Webb Space Telescope opened its mirrors. It now sits far beyond Earth, positioned in a gravitational balance point where the Sun, Earth, and deep space allow it to remain shielded from heat and interference. From that cold, distant vantage point, its instruments collect ancient light that has been traveling across the expanding universe for billions of years. Each photon it records is not just an image, but a message from a time when the cosmos was young. Looking deeper into space is not simply looking farther away. It is looking backward. The greater the distance, the earlier the moment being observed. At the most extreme ranges, the telescope is examining regions that existed only a few 100 million years after the beginning of cosmic expansion. Before Webb, the expectation was clear. The early universe should have appeared dark, sparse, and dominated by small, simple structures. The first stars would ignite slowly. The first galaxies would begin as faint, irregular clusters gradually growing through mergers and gravitational accumulation. Complexity was supposed to take time. Instead, the first deep observations revealed something that did not fit that quiet narrative. Where astronomers expected to see scattered fragments of young galaxies, Webb began detecting systems that appeared surprisingly large, bright, and organized. These objects were not impossible according to physics, but they were far more mature than many simulations had predicted for that stage of cosmic history. Some of these galaxies appear at redshifts, indicating they existed when the universe was only a few 100 million years old. Their light shows structures that suggest significant star formation had already occurred. In some cases, the inferred stellar mass is much higher than models anticipated for that epoch. It is not that the universe broke its own rules. It is that the timeline may have been more efficient than expected. Earlier telescopes could only hint at these distant objects. Their sensitivity was limited, their resolution blurred. Webb, operating in infrared wavelengths, can see through dust and detect faint signals stretched by cosmic expansion. Suddenly, what once looked empty revealed density. The surprise was not the existence of galaxies. It was how quickly some of them seemed to assemble.